Okay, so here's part three of our discussion on acid base. And we'll talk in this part about acids and bases that are formed from other substances. But first, we can start off with a little bit about how antacids work, right? So you look at these antacids and you see that each of them has some way of creating OH minus, and again, antacid meaning that they're going to take away the acid, and then we know that this is a base and it creates OH minus in water. Okay, and so it basically soaks up the H plus. And these are the ones that you may have used, you've seen, your parents have used, etc., right? And all of these contain compounds from that previous slide. So I mentioned this a little bit earlier, a little bit about relative strengths, right? And if you look at the top here, you'll recognize the strong acids, and then you look in here, and you've got the weak acids, and then you look at the bottom here, and these are considered negligible, meaning that they don't really do anything, right? They don't create any kind of acid. And then over on this side, we've got all these weak bases, right? We have some strong bases down here at the bottom, right? And then we have relatively neutral species up here at the top, right? So the question of, do saltwater solutions have a pH of 7? And the answer to that is no, right? They're made up of a salt, and so they have a cation and an anion, and oftentimes one of those is going to influence the pH. So a couple of different ways that we can approach this. Let's start off with the neutral solution, right? If we talk about a neutral solution, um, we're talking about something that if you look back, strontium hydroxide, right, SrOH2, right, that was a strong base. So the counter ion, right, the strontium 2 plus, is a weak and not even weak acid. It is a non-acid, right? So strontium coupled with, and then Cl minus was part of HCl, and HCl is a strong acid. So again, part of a strong acid, part of a strong base, they go together, and they're going to be neutral. Okay, so let's look at the situation where we have an acidic cation. So where did this cation come from, right? So this cation was from a CH3 NH2, right, in solution water, picking up a proton and becoming CH3 NH3 plus, right? And sorry, this is a plus sign, plus OH minus, right? So that was a base. That means that this CH3 NH3 plus is the conjugate acid, right? So it's an acidic cation. But NO3 was originated from HNO3, which is a strong acid, meaning that NO3 has no real basic quality to it. And so this would be acidic. Okay? Other side, you've got Na from NaOH doing nothing. You've got this COOH basic anion, and that is actually, I'm sorry, HCOO minus, and that is actually from CH2COO, right, or CH002, right, with another proton on there. Okay. Um, it actually, sorry, it would look like this, right? OH, right? If it had the H on there, and then you'd have an H here. Without this, right, which is what this is, it's got a minus sign, right? And so this came from the acid COOH, and so therefore it is basic, right? It is the conjugate base, and so again, this solution would be basic. Now here's the tough one, right? Where you've got an acidic cation and a basic anion. What happens? Well, they fight over it, right? So it depends on who is stronger, and so you would have to compare um, the K, the KB, and the KA. So in these cases, we would use ice tables similar to what we would use before. Look at the equilibrium conditions, and there's the solved ice table. Okay. So in this section, we're going to look a little bit at the strengths of acids and bases. Again, we looked a little bit at that when we talked about weak acid, weak base. We're going to do a little bit more on that. So the strength of acids and bases can depend on the difference in the um, partial charges of the H plus and whatever it's attached to. Okay. So the bigger the difference, the easier it is for this H, for the H plus to vominos, right? So you got three different choices here, right? This one actually wrong direction, right? Not acidic. In fact, the lithium has a more positive charge, but on this HF is acidic, and then the electronegativity difference between H and carbon is insignificant, and so it really does not form any kind of dipole. So electronegativity, the increasing electronegativity is going to increase the acidity, and then on the on so that's kind of on the x-axis, if you will. On the y, right, the decrease in bond strength is going to increase acidity. Okay, and so too big, right? Too big a electronegativity. Down here, electronegativity is still high, but this decrease in bond strength between H and I then leads to a increasing. So this table shows it. The bond energy or bond strength, you get this really strong bond here, HF, weak acid. Relatively smaller, strong acid. Even smaller still, strong acid. So in general, you could describe this for the hydrogen attached to an oxygen that is then attached to another ligand. We could look at the electronegativity differences and describe this. So as these electronegativities go up, the Ka gets bigger, right? Structure also makes a difference, right? In this one, you've got the Y being the Cl, but in the first case, you've got these three oxygens pulling on the Cl, creating a bigger difference. It's a strong acid. You only have two here, and it's not a very strong acid. You only have one here and none here, and so a very weak acid, right? So the question is, who's the stronger acid, right? So again, take into account um, who's pulling on the carbon, and if you have hydrogens pulling, you know that there's no real electronegativity difference in these hydrogens, but there is here, and so this one, right? answer revealed. Again, only hydrogens, right? Therefore, not as big. So we talked a little bit about Bronsted-Lowry, and we've kind of been, dabbling in both Arrhenius and Bronsted-Lowry because Bronsted-Lowry is focused on the proton production and on the proton being attracted to bases, right? So proton donor, proton acceptor. The Lewis model looks at electron pairs. So briefly, with this comes a difference in the electron pairs pulling at a central atom, and so the loose electron pairs create the acid and base differences. Just an example of Lewis acid, Lewis base chemistry. We're not going to go into this. We can talk a little bit about water as a Lewis acid and carbon dioxide. I'm sorry, water as a Lewis base and carbon dioxide as a Lewis acid. And the reason that this is important is because of the production of carbonic acid. So, I mentioned climate change. Climate change, we have a large production of CO2 from the burning fossil fuels. That CO2 is being dissolved in the water, and as it's dissolved in water, it creates carbonic acid. This decreases the pH of the oceans, and again, the most dramatic effect is on the coral reefs and on shellfish because they are made up of carbonate, and carbonate is part of then this carbonic acid cycle, which means that more carbonate goes into solution to offset that equilibrium. It's an exceedingly difficult problem. We need to stop burning fossil fuels. A lot of metals behave like either Lewis acids or Lewis bases, so you'll see that quite a bit. And again, the water acting as a Lewis base in this case. We also have a problem with acid rain. You've probably heard of that before. And again, these statues are typically made up of some kind of carbonate, and they're being dissolved, as well as massive problems with forests and trees dying off from acid rain. So SO2 is something that is involved in that. So when SO2 goes up into the atmosphere, we eventually get H2SO4 that falls out because when it gets into the atmosphere, it is mixed in with water as rain and comes down. And, back in the 90s-ish, big problem in many of the cities where cars were being pitted by actual acid rainfall. It's still a problem, but as you can see, there has been a reduction up until 2010, and that continues. Okay, so let's review. When we started off, we started looking at whether or not we could predict whether something was acidic or basic given information about H3O plus, OH minus, pH, or POH. And indeed, we were able to do that and do it pretty effectively. And then we looked at strong acids versus weak acids and said, look, the strong acid completely dissolves, and it dissolves into strong acid completely dissolves into H3O plus and NO3 minus, right? But a weak acid, there's still some of the original acid around, as well as the H3O plus and the F minus. Another example of a weak acid, right? And here's an example of a strong acid. Weak acid, incomplete dissociation. Strong acid, complete dissociation. weak acid incomplete, strong acid complete. Let's talk about strong bases versus weak bases, what they look like. We look at ABC. In A, we still have some of the original ammonia hanging around. Incomplete, we look at NaOH. Complete, we look at SR2 plus OH minus, and it's complete. Weak base, incomplete. Strong base, complete. Strong base, complete. So let's talk a little bit about binary acid strength, right? We talked about that earlier. Let's review it. We noted that the acidity increased as we went to the right because of higher electronegativity, but then it decreased as we went down. I'm sorry, it increased in acidity as we went down because of a decrease in bond strength. Okay, so this guy was not able to hang on, right? Couldn't hang on to the H quite as well. On to oxyacid strength. So in oxyacids, the strength was relative to the electronegativity of the Y group, right? And so the stronger the electronegativity of the Y group, the harder it is to hang on to that, the bigger the Ka, so the stronger the acid. Structure played a role, and the way that it played a role in this is what the chlorine was bonded to made a big difference, right? So this one's strong because it had 3 oxygens. We had a Ka of 1 because of 2 oxygens, and then it just goes down from there, right? The Ka gets smaller and smaller. We talked a little about the pH of salt solutions, and that pH had to do with where these came from, right? So again, if they came from a strong acid, then their strength was lower. If they came from a weak acid, their strength was higher. And the same thing with bases. So we had the neutral because it came from a strong base and strong acid, therefore a neutral came from a base, therefore acidic. Hang on. Yeah, sorry. The K from a KOH, which is a strong base, the F from HF, which is a weak acid. And finally, this discussion of, I might have skipped one. And finally, this is where we started this whole discussion with Arrhenius, Bronsted, Lowry, and Lewis, and understanding how they all play together.